My name is Kniazeva Kseniia, so thank you for the introduction. And also I want to say thank you to Anastasia and Gennady and all the organizers of this workshop for giving me the opportunity to have a talk here. So I work under supervision of Andrei Shanin, and as he promised yesterday during his talk, I will tell about the multi-contour saddle point method and its application to the description of the transient processes in waveguides. The first part of my talk is the matrix Klein-Gordon equation. So we consider a waveguide system composed of several roads. These roads are continuous, and these roads are linked by elastic layers. The longitudinal coordinate is x, and the field in such a system can be described by the state vector u, which is composed of the displacement in each road. So the number of roads can be more than 2, and I will show examples. So each road supports only one mode. And the wave propagation in such a system is described by the matrix Klein-Gordon equation. It's written here. Matrix coefficients d2, d1, d node m should obey these properties to provide that kinetic and potential elasticity energy are positive. And this equation can be derived from the governing equation of continuous from media equations, and also it can be derived from a finite element method model for a waveguide. So we can cut a wave. It's a standard approach to study a waveguide. We can cut a waveguide into slices to apply finite element method to one slice to put Flaquet boundary conditions on its cross section, and we can study its dispersion diagram. So both matrix Klein-Gordon equation and finite element method are consistent in this case. And also let me note that this equation is quite standard in studies of waveguides, and it can have other names. Also, it's called waveguide theorem, wave theorem, and so on, and also semi-analytical finite method. This equation has different applications, such as tires, boreholes, and rails. Here are some examples only. And we consider only pulse force sources, which is applied only one point. And this force is put here on the right-hand side.
May I ask a question?
Yeah.
How have you broken the symmetry in X? Is it through the springs?
It's longitudinal.
Yeah.
The waveguide is continuous along the X value.
But you have a D1, so you have X is not symmetric. So how do you break the symmetry?
Well, this term exists in waveguides where for example, in elastical waveguides, when longitudinal waves interact with the transversal modes, or in electromagnetic waveguides when the electric field interacts with magnetic field.
Thank you.
So it's not difficult to find the solution of this equation. We need to apply the Fourier transform in X and Laplace transform in T, and as a result, we obtain such algebraic equation. B is a matrix, it's written here. And to find the field, we need to apply the inverse transforms, and we get the field representation in the form of double integral over frequency omega and over wave number k. So we are going to fix k and to calculate the inner integral using the residue theorem. To do that, we need to enclose the integration contour in the lower half plane according to the Jordan's lemma, and then we apply the residue theorem. So to find poles, we need to consider that the integrand includes the inverse matrix of B. It can be presented as the ratio of the adjacent matrix over its determinant. To find the poles, we need to solve this equation. So the determinant of matrix B should be equal to 0. This is a dispersion equation, and this equation gives us poles. And from the properties of matrix coefficients, we can derive that for real k, we have only real solutions of the dispersion equation. So that means that all our poles live on the real axis. As a result, after we apply the residue theorem, we obtain this representation, and it can be transformed to the standard field representation in the form of model composition. Here, V is a right-hand eigenvector, and V is the left eigenvector of the problem. But in the following, we will use mainly this representation. So the next part of my talk is we are going to consider our integral representation on the complex dispersion diagram. So what it means. Instead of considering different solutions of the dispersion equation, we can consider a multi-valued function omega of k, which is defined implicitly by the dispersion equation. And this multi-valued function, omega of k, has a Riemann surface. It's schematically shown here. So we have a number of sheets, and they are connected with branch points and some cuts between them. So now, instead of integrating over the real axis of k, we integrate it on the Riemann surface. So we have a set of integration contours, and they go along the real axis of k. So they are like imaginary images of the real axis k on the Riemann surface. And on this surface, we still can use the Cauchy theorem if we take into account the branch points. So we can deform the contours only in the area of analyticity of the integrand. So that's a problem. To avoid this problem, we can propose to consider the integration not on the Riemann surface. We can consider instead the set of all solutions of the dispersion equation. We call this set H. And consider our Riemann surface as just a projection of this full complex dispersion diagram onto the k-plane. So our branch points appear as a result of this projection. And the set of all solutions of the dispersion equation is a complex manifold, because our dispersion, the left-hand side of our dispersion equation is just a polynomial. So we can move freely, or we can deform our integration contours freely on this surface. So now we get a field representation in this form. And the integrand is the differential form. Here it's written for local variable k. and also it can be, we will use its representation for local variable omega in case we are near the branch point here. And now we are going to find asymptotic estimation for our representation. It's written here again. We are looking for asymptotic for large x and for fixed formal velocity v. Formal, so it's a ratio of the coordinate x over time t. So we see that the integrand includes the exponential factor, and let us transform it a little. We have we obtain the phase function g. And our goal is to deform contours in the direction of growth of the imaginary part of this phase function, so that these blue arrows show us the direction. So as a result of this procedure, we deform our initial contour, which is red, into a set of saddle point contours, which are green. So these contours go through saddle points, and for integrals along these saddle point contours, we have an analytical formula. So it's so our goal is to represent the field as a sum of saddle point contours. And since the complex dispersion diagram is smooth, so we don't have any problems with that. So now here I put the formula to find the saddle points. To find them, we need to find the derivative of the phase function and put it equal to 0. And as a result, if we substitute this formula to this formula, we obtain that the group velocity should be equal to the formal velocity. So we are looking for such points. So in practice, we need to deform 1,000 contours, and as a result, we obtain thousands saddle point contours, and it's difficult. Instead of that, we propose to find all the saddle points firstly, and then we decide which of them are active or not active. Let me explain what does it mean. It's a common situation for waveguides when for some value of formal velocity, we have two saddle points on the real axis, for example. But if we slightly change the formal velocity, instead of two saddle points on the real axis, we obtain two saddle points in the complex domain like this. And in the first case, our initial integration contour, which was along the real axis, deforms into these two saddle point contours. But in the second case, we obtain that our initial integration contour goes upward, so it only hits one of the saddle points. So this point is active, and this one is not active, although both of them are solutions of the equation here. And as an example, it's written an area function here. So its initial oscillating part is described by these two saddle points, and the attenuating back part is described by this point. So we propose to find all the saddle points and for all values of v now. So consider, for example, 2 points from the previous slide, And then we slightly change the value of formal velocity v, and we don't clean the previous saddle points. We put another point here. So we continue this process, and as a result, we obtain a set of curves. So that is, again, the set of all saddle points for all values of formal velocity, and we call this set a carcass of the dispersion diagram. So we are going to plot a carcass, then we going to divide it into active and not active points. Here I show the algorithm how we can decide which points are active and which are not. So this picture was shown earlier. So, and the idea, we can try to restore the this blue line, which went from the initial contour to the saddle point. So consider one of saddle points, one of the carcass points. Then we plot two lines of a decreasing of imagery part of G function, and we look what we have. We can obtain three cases. We stop at the points when the imagery part of G equals to 0. And three cases are possible. In the first case, the final points are not on the initial contour. This point, so that means that this saddle point is not active. The second case is when the flows, we call these blue lines flows, when the flows goes to the initial contour, and this is also bad. This means that the point is not active. And the last case is when one of the flows goes to the initial contour and one of them goes not there. And this means that this point is active. And let me note that there is also a scientific group. Here is the related article of them, and they proposed a similar algorithm, but they work in other area of physics, and their article were published later than ours. So now let me go to the examples. Let's consider a simple example. So the matrix coefficients have dimension only 2 times 2. So we have only 2 rows. Here, so we took just like some values here. And for this system, real dispersion diagram looks like this. And the Riemann surface has 4 sheets, and it's plotted here. So each panel is a copy of the K-plane, and I cut this surface in such a way that each curve of the real dispersion diagram lives on one panel. So the orange curve lives on the orange panel, the violet curve lives here. And we plot the carcass for this system. It's plotted by red and blue. We see that the real axis of K is also belongs to the carcass. It's quite obvious. Parts of the imaginary axis belong also to carcass, but they are not active. And we have interesting part here. So we observe. So we plotted complex carcass branches, and they also form some pulse in the waveguide. And these complex carcass branches start from the real axis at the points where the group velocity has local extremum. So these points also called area points, and it's related to the area asymptotics. So now let me consider another problem. It is similar to the previous one, and even the real dispersion diagram and group velocities look similar. So here I plotted only, these figures are only for positive omega and k. So again, the group velocity has one maximum, one minimum, but the carcass looks differently. It's shown here. So again, the blue points are active, the red ones are not active. Here is another example. So the main feature of this system is that the group velocities are monotonical. So we don't have any active carcass branches which started from the real axis of k. Instead, we have something looking like a circle. And there are also active points on these circles. So our initial motivation was cut tires, and actually it's a resonator, but if you hit it by a point source for some time, we can observe waveguide propagation in such tires. So now the longitudinal coordinate is phi, and for a real tire, phi takes values from 0 to 2 pi, but now we consider that phi can take any real value. So, and this waveguide tire can be described also by the matrix Lane-Gordon equation. And since a cut tire is a complicated structure, the matrix coefficients have the size 3000 times 3000 approximately. So we cannot deform for such a system in contours. Our method is more efficient. So here is the real dispersion diagram for a tire. It looks complicated. And here is the projection of the complex dispersion diagram on the three-dimension space of real k, imaginary k, and real part of omega. So the Riemann surface has sheets. We can see them. Some of them are slowly, some of them are fast, and so on. So, and here we plot the carcass for a real tire. Again, the blue curves are active branches of carcass, and the red points are not active. And here, I'm so sorry. This is the same figure as it's here, but it's plotted by blue. And I just wanted to show that the pink points on this, it's the points of the carcass. So this is all. Actually, so now let me make a conclusion. So we proposed a multi-contour saddle point method. We have an algorithm to find a carcass for any waveguide, which is described by matrix Lane-Gordon equation, and we have an instrument to classify it. So, and here are the links to our papers on this topic. So, thank you.
Thank you very much. Thank you. Very nice talk indeed, and you've given us time for questions, which is great.
Thank you, Kseniia. Very interesting talk. Sorry if my question is a bit of naivety or I missed something. In the very first equation, you have the term D1,
Okay.
which is I expect to be viscosity. If that term is not small, nothing can propagate. Okay, so is it any assumption? And then in later plots, it was dropped completely when you presented your dispersion relationship. Why is that sort of?
It's not the viscosity.
No.
Your divine is a matrix, and it is anti-symmetric.
It just breaks the symmetry in X. So when it's 0, this is symmetric. So all of your phase diagrams are symmetric in K,
So,
in K space. So it's fine. No, if you had a derivative in t, then your point would be
Okay.
Yeah.
D1 is antisymmetric. Right?
anti-breaks the symmetry.
No,
Yeah,
D1 transpose is minus D1.
yeah.
So D1 is missing.
Yeah, all your examples had no d1.
Okay.
Yes, but for tires it exists.
Yeah, so maybe it does. But,
Oh,
but
yeah,
the tie
yeah,
you
that's it,
showed
yeah.
was still symmetric in k
Yeah.
to reflect the fact that d1 was there at 0 as well.
This is the key, right? D1 equals minus D1 T,
Yeah.
right?
Yeah,
So to
That's
preserve
right.
the energy.
Okay.
yeah.
So just out of curiosity, is there a way to generalize this approach if you have more than one special coordinate?
If
If you
more
have a
than
series
one
of x,
special
you have x and y, or x and y and z.
Oh, we did it actually for waveguides for one longitudinal coordinate.
Yes.
I'm sorry, I didn't think about it.
Okay.
Mike?
Lots of questions, but I'm trying to understand in your contour, you go from minus infinity to infinity, then you go onto these Riemann sheets. What's the topology that you can get back to infinity? Your contour has to return to where it started.
Are you asking about the criteria of classification of points?
No, you convert this contour, you have an interval from minus infinity to infinity,
Yes.
you're inverting it, and you go onto these Riemann sheets.
Yes.
Right? But you've got to get back, the contour goes from minus infinity to infinity, so it comes back to itself. I can't see how the contour on the Riemann sheet returns. Maybe I'm missing something.
I'm sorry, I don't understand.
All right.
What were you asking?
And it's maybe another question. When that diagram, the curves touch, right?
Yes.
You draw them as though they didn't touch in one of those pictures, but like on slide 20, I think. Yeah, 20. Q0. Slide 20.
Okay.
Yeah, those curves there, the pink and the green touch, but so how do you tell which branch you're on? When they actually cross there, or do they repel?
Oh, I'm sorry, yes. There is a avoiding crossing here.
Oh, so they never touch?
Yes, yes.
Oh, okay.
It's a common effect when your model branch interact, they avoid the crossing.
But they don't touch, they actually have a gap.
Yes, yes. I'm sorry, I thought it would be clear that if I plotted the curves with different colors, so
Yeah, no,
I'm
I
sorry.
thought they touched. Yeah, okay.
Yeah.
Yeah. All right.
So may I ask a final question? I've got 20 seconds. But for the real problems where you have the tire, extremely complex, very, very delicate dispersion relations, how stable is that? If you just change the parameters slightly, does it mean that the results will be very different?
well, I don't know.
Yeah, the structural stability of your solution may be very delicate or not.
We
hope it
considered
would.
how the carcass changes with changing of parameters for simple systems, but for tires it's difficult to follow all the changes of such a difficult, complicated carcass.
But we've run out of time.
David, when you started your question, I thought you were asking about motorcycle tires.
I know. I'm sure there's plenty of us who have an interest in that.
Looked like a motorcycle tyre, clear. I
Yeah.
thought.
Yeah, but we need to finish there. Thank you very much for an excellent talk. Thank you.